Hello, I'm Otitochi from Special Maths Academy, and in this video, we'll be solving the problem 4 from the NMC fourth round. So in this geometry problem, you are given PT as PB as tangents to a circle and point A as the point diametrically opposite B. Also, H is the foot of T on AB, and then you're asked to prove that AP bisects TH. So I have a diagram of it here, or a construction of it here. I'll be working with this. So basically what we want to show is that TY is equal to TH, where Y is the intersection point of AP and TH. Also, let's call X the second intersection point of AP and the second circle of ABT. So like I said, what I want to show is that TY is equal to YH. Right, this is what we want to show. Right, so or in short, that TY over YH is equal to 1. Right, this is what we want to show. Right, so this is a geometry problem. So first we'll start with basic angle chasing and see what we can find. Right, so what do we have? First, let's start with the obvious ones. Since AB is a diameter, we expect angle ATB to be a right angle. Also expect angle AXB to be a right angle, and H is the foot of T on AB, so we are expecting a right angle as well here. Also, if this angle here is alpha, if angle TAX is equal to alpha, then expect angle TBX to be equal to alpha as well. And also, if this is beta, then here has to be beta as well. Right, so that's about that on what we can get. Also, since this is a tangent, since PT is tangent to the second circle of TAX, we are expecting angle PTX to be equal to angle TAX. So here is alpha, and similarly here will be beta as well. Right, so that's about I think that's the basics angle chasing we can do. But let's let's focus on what you actually want to show. I want to show that TY over YH is equal to 1. That's what we want to show. Right, so let's think about how we want to do that. So the best way to represent TY and YH is with trig, right, with trigonometry. So let's start by considering these two triangles, TAY and HAY. Let's start by considering those two triangles. So we know that TY over sine alpha, that's sine angle TAY, is equal to 80 all over sine angle AYT. Right, so this implies that TY is equal to 80 sine alpha over sine angle AYT. Now we have succeeded in representing TY in trig form. So let's try YH. We'll do something similar with YH. YH over sine beta is equal to AH all over sine angle AYH, which implies that YH is equal to AH sine beta over sine angle AYH. right? So now we can now express ty and yh. So we have ty over yh is equal to, we have 80 sine alpha multiplied by the denominator of this, which is sine angle AYH, all over AH sine beta multiplied by the denominator of this, which is sine angle AYT. Now, of course, as you may notice, AYT and AYH, they are on a straight line, right? So they sum up to 180 degrees. So their sines will be equal. So sine angle AYH and sine angle AYT here are going to cancel out to just leave us with 80 sine alpha over AH sine beta. Now this is equal to ty over YH. Remember that what we aim to show is that ty over YH is 1. So basically what we want to show is that 80 sine alpha over AH sine beta is equal to 1. So it's always good to have a goal in mind, because we always so that we'll be able to know which is the best next step to take, right? So our goal is to show that 80 sine alpha over AH sine beta is equal to 1, or 80 sine alpha is equal to AH sine beta. So how do you go about that? First, how do we deal with sine alpha and sine beta, right? Those are trig values. So one way or the other, we have to find a way to deal with them. So to do that, let's look at triangle XBT here. Right, these are points X here. And when I say let's look at that, because I think that's the only triangle here that contains alpha and beta, both alpha and beta as angles, right? So why it's of interest is because we can represent sine alpha using the sine law. We can represent sine alpha over sine beta as tx over bx, right? So once we do that, this basically means that ty over yh is equal to 80 over ah times tx over bx. Now you have gotten rid of the trig, right? So basically we just need to show that 80 times tx is equal to ah times bx. That's our goal. But also another thing we may want to notice now is what we haven't really used is this configuration here. This is a popular configuration, and I think it's related to the Euler's theorem. So we have A, T, B, and H. A, T, B, and H. So now, whenever we have this configuration, it can be easily proved with similar triangles. So Euler theorem is telling us that TH squared is equal to AH times HB, BT squared is equal to BH times AB, and AT squared is equal to AH times AB. This is what Euler's theorem is telling us. Can easily prove that using similar triangles, because triangles ATB and triangles ATB, triangle AHT, and triangle THB are all similar. So now when you use similarity ratios for these triangles, for example, if we pick ATB and AHT, we can easily get AT over AH is equal to AB over AT, and this will imply our third the third part of Euler's theorem, which tells us that AT squared is equal to AH times AB. Right, so we can show all of them with similarity, but what is actually of interest to us is this part that tells us that AT squared is equal to AH times AB. Why? Because that will help us deal with AT over AH, because it's going to imply that AT over AH is equal to AB over AT, and this will mean and this will be equal to AB times TX over AT times BX, right? So that's why is that's where this configuration comes into play, and that's why it's actually pretty important to be able to recognize this kind of configurations head on. So it was the Euler's theorem I used here, and I showed how to prove it. So let me erase this for now so we can continue with our solution. Now you are trying to show that AB times TX is equal to AT times BX, right? So if you may notice, you can actually notice that AT, AB, TX, and BX are actually sides of a quadrilateral, right? And basically AT and BX, AB, and TX are opposite sides of that quadrilateral. So if what you are trying to prove is actually true and this is one, then such a quadrilateral is called a harmonic quadrilateral, where the product of opposite sides are equal. So we are trying to show this, right? We are trying to show that ATXB is a harmonic quadrilateral. So how do we show this? This is where tangencies come in. This is where our tangencies come in. So because PT is tangent to the second circle of ATX, we actually have like we used that before to show that here is equal to alpha. But what we are going to use now is the fact that triangle PTX is similar to triangle PAT. Right, so this will imply that PT over PA is equal to PX over PT equal to TX over 18. Right, so but what is actually of interest to us is the fact that PT over PA is equal to TX over 18. Or we can rephrase this as okay, let's leave it like this, PT over TA, right? So similarly, you are going to get that PB similarly, when we do something similar with triangles BAX and PBA, we'll end up with we'll get PB this time over PA is equal to BX over AB. Now you're basically done, right? Why? Because from this, we can get that TY over YH is equal to AB over BX, right, times TX over 80. Right, I switched some BX and 80 here. So we have AB over BX times TX over 80, right? So this is equal to, now AB over BX is equal to PA over BP from here, times, now TX over 80 is equal to PT over PA. Now, PA cancels PA, and we are left with PT over PB. But PT and PB are tangents to the circle from P, right? So they are both equal. PT is equal to PB, so then we have equal to 1, which was what we wanted to show, right? So this implies that TY is equal to YH, right? And we are done. So that's that for this problem, and thank you for watching this video.